All right, so today we will continue our discussion on network growth models. So in the last lecture, we have briefly talked about, some of the properties that real world networks follow, right? For example, small load property, power law degree distribution, right? And clustering coefficient is also significantly high with the increase of number of nodes, right? And then we discussed a very simple network growth model, which is called random network growth model. And there we have seen that the degree distribution doesn't follow power law. It basically follows Poisson distribution when n tends to infinity, or a normal binomial distribution, right? But interesting property that we have noticed is that random network has random network follows small world property, in the sense like the average path length, okay, is proportional to log n, okay, where n is the number of nodes. We have also seen that a random network model does not follow the clustering coefficient, real world clustering coefficient property, in the sense like if n increases, clustering coefficient will almost be same. The clustering coefficient is always quite higher, but in case of random network, we have seen that if we keep on increasing n, average clustering coefficient decreases. Okay, so that is the last property. The property related to clustering coefficient is something that we will address here in today's class, right? So we will see that we'll discuss some of the models which particularly were designed to sort out the problem of clustering coefficient issues that the random network model suffers from. Okay, so we'll discuss today something called ring lattice network. Okay, so ring lattice network is again a kind of an advanced model compared to the random graph model, right, which was designed in such a way that the clustering coefficient property, real world clustering coefficient property, will be preserved here. Okay, now let's look at the design principle of ring lattice network. What was the design principle of random graph model? In random graph model, we basically in that G n comma p, right, G n comma p model, we had n nodes, and we choose a pair of nodes, and then we toss a coin with probability p, we connect them, with probability 1 minus p, we do not connect them, right? That was a very simple idea. In ring lattice network, let's assume that it looks like this. Okay, so it forms a ring. Okay, and each node, right, each node, say v, is connected to, and let's assume that the degree of each node is always fixed, which is k, right? So it's a regular graph in that sense. Okay, so degree is fixed. And how the neighboring nodes are connected? The neighboring node the connection of neighboring nodes for a particular node follows a particular principle. What's the principle? The principle is that the node v is connected to k minus 2 number of neighbors in its left side, and k minus 2 immediate neighbors, right, to the right side. Okay, very simple. So if k equals to, say, 4, that means this node is connected to this node and this node in the upper side, and in the lower side it is connected to this node and it is connected to this node. Okay, so you see degree is 1, 2, 3, 4. Now this is the connection principle for all the nodes. Okay, so you take a node and the degree is k because it's a regular graph. You connect k minus k by 2 immediate neighbors in the left side and k by 2 immediate neighbors in the right side. Okay, now this is called a regular ring lattice. Okay, this is a regular ring lattice. So I hope the design principle is clear, right? How this network is formed. Okay, now the question is, in this particular setting, what's the average clustering coefficient? Average clustering coefficient of a node. Okay. So this is a little bit tricky, but please follow the the instructions properly. You will understand it. So when we measure the clustering coefficient of a node, right? What are the two things that we measure? One is the actual number of nodes among the neighbors, and it is divided by the possible number of neighbors. Okay. So there are k minus so actual number of neighbors, and the possible number of neighbors. Actual number of edges between neighbor and possible number of edges between neighbors, right? So possible number of edges among the neighbors is fixed, which is k into k minus 1 by 2. There are k number of neighbors, so possible number of edges would be k into k minus 1 by 2. Now let's look at the actual number of edges among the neighbors in this particular graph. Okay. In order to do so, let's look at let's unfold this graph. Okay. This is a kind of a circular graph. Let's unfold it, right? If we unfold it, say this is V, okay, and you have, right, you have, okay, so this is V, say this is V1, V2, V3 dot dot dot. So how many number of neighbors are here? K by 2, right, till this part, and here also K by 2, right? Right. So now let's look at, so what we are interested in? We are interested in measuring the actual number of edges, right, among this set of nodes, right? Okay. So the induced subgraph formed by the neighbors of this particular vertex. Okay, and we look at the number of edges there. So let's look at it. Okay. Now for V1 also has k by 2 connections in this side and k by 2 connections in this side. Okay. So these connections we are not interested in, because these connections are not part of V's degree, right? So we are, because this is the last vertex. Okay, this is the last neighbor in the left side of V, and this is the last neighbor in the right side of V. Okay, so we are only interested in nodes among this particular edges among these particular nodes. Okay, so so let's look at it, right? So V1 has k by 2 connections here in this side, right? K by 2 connections in this side, right? But please remember one thing, that when we measure clustering coefficient, for example, right, of this vertex V, right, we do not consider the edges which are directly connected to V, right? We do not consider this edge, and this edge. Remember this. So therefore, say if this is V and this is V1 in this context, this is V and this is V1, so the edge which is connected from V to V1 will not be considered, right? So therefore, how many nodes, how many edges we will consider to measure the clustering coefficient of V which are associated with V1? K minus 1 by K by 2 minus 1, right? K by 2 minus 1. What about V2? V2 also, right? Now think about it. In case of V2 has one, again, K by 2 edges in the left side and K by 2 edges in the right side, right? So we will consider all the edges coming from V2, and remember, one edge from V2 will be connected to this node, right? We have shifted one side in the right side. So how many edges will be connected? How many edges will be considered in this case with respect with V2? Again, k by 2 minus 1. Right? So on and so we will basically do the same thing for all the nodes which are in the left side of V till this part. Okay, till this part. And remember, when we consider this node has already been connected to, this is already connected to other nodes. Okay, and this node as well. So total number of edges that we consider for each left side node is k by 2 minus 1. So how many such left side nodes are there? K by 2. So k by 2 into k by 2 minus 1. This is the number of edges that we consider with respect to the left side nodes, left side neighbors of V. Okay, so this part is done. Now let's look at the right side nodes. Okay, so now this is very interesting. Right side, let's look at this node. Okay, so this node, what has happened? For this node, this particular edge has already been considered. This edge has already been considered. Okay, now this node also has k by 2 nodes, k by 2 edges in this side and k by 2 edges in this side. Okay, so now tell me, for this node, for this particular node, how many edges we will consider for this node, which is the immediate right neighbor of V? Tell me. For this node, how many edges will be considered?
K by 2 minus 2.
Why k by 2 minus 2?
Because towards the right, we consider.
Why k by 2 minus 2? So this node has k by 2 edges in the right side, right? But we ignore one because the rightmost neighbor, the farthest rightmost neighbor is not a part of V's neighborhood, right? So k by 2 minus 1, because we are not considering any node in the, any edge in the left side. The left side edges have already been considered. We are considering only these nodes, right side neighbors, right? And how many neighbors will be considered to calculate V's clustering coefficient? K by 2 minus 1. Think about it. Okay. What about the next one? The next node, k by 2 minus 2 dot dot dot. If you look at the farthest rightmost neighbor of V,
Zero.
0, right? So 1 plus 0, right? So what's the sum here? K by 2 into k by 2 minus 1 by 2, right? So total number of edges that we'll consider is this plus this. Total number of edges among the neighbors, k by 2 into k by 2 minus 1 plus k by 2 minus 1 by 2. So that means 3 by 2, right? 3 by 4. 1 plus 1 by 2, 3 by 4. k by 2 minus 1, right? 3 by 4 k into k, because 1 plus 1 by 2, 3 by 2 into 1 by 2, 3 by 4 k into k minus k into k by 2 minus 1. This is the actual number of ages among the neighbors. This is the numerator. And what's the denominator? The denominator is k into k minus 1 by 2, right? So this k and k will cancel out, right? So we have 2 here. So if you do calculation, this would be 3 into k minus 2, right? 4 into k minus 1. So this is the clustering coefficient. Now, if you find this part a little bit complicated, my suggestion is that go back, take a small example, say k equals to 5, for example, or k equals to 4, right? And you do this calculation, you will understand why this thing, and then you try to generalize it. Okay. So the average, so the clustering coefficient, local clustering coefficient turns out to be this one. Okay. So as you understand here, as k tends to infinity, these and these will cancel out, because k minus 1 and k minus 2 will be almost same if you increase k. So this would be approximately equal to 3 by 4, right? So what it is saying? It is saying that for a large lattice, right, the local clustering coefficient is always high. Okay, it is always 3 by 4, and 3 by 4 is pretty high. Clustering coefficient ranges between 0 to 1, right? 3 by 4 is pretty high, right? So in case of ring lattice network, the good part is that it kind of follows the clustering coefficient oriented, the behavior, the real world behavior with respect to the clustering coefficient. Okay, but what's the problem? The problem is that it's a regular graph. So regular graph doesn't follow the power law distribution. The degree distribution would not be power law, right? But anyways, to just overcome the problem of clustering coefficient, this was proposed. The ring lattice network model was proposed. Now let's look at the next model. Okay, so so what we have learned so far is that in random network follows small world property, right? The lattice model has high clustering coefficient for large network, but it does not follow small world property. Okay, so now you know how to address both these problems together. Okay, so in around 1998, 1999, two scientists, Watts and Strogat, okay, they proposed a model which is called Watts-Strogat model. Okay, now Watts-Strogat model, so it is not a particular model, it is basically a suite of models, and the idea is that you start with a regular graph, you start with the regular lattice, the one that I mentioned, right? And you do some modification so that the extreme case is a random network, right? So there are two extreme cases. One is a regular lattice, which is a regular graph, right? Very well formed regular graph, and in the other side you have a random network, which is very non-uniform, right? Which basically happens randomly. All these edges appear randomly. Now, in between two spectrums, right, you see a lot of small substructures of the network. Okay, now let's see how we can address this problem. Okay, let's look at this one. Right. So the idea is that you start with a regular lattice. Okay, you start with the regular lattice, and in the regular lattice, the P is again the probability of rewiring. Now, what do I mean by revarying? Revarying means revarying probability. Probability is P. What does it mean? It means that in this ring lattice network, you choose a particular node, right? And you choose a particular edge which is associated with the node, right? And you reware the edge in a different way. Say, for example, you choose this node, right? And you choose this edge. Okay. Now, when you reware it, it means that instead of connecting this edge with this node, you connect this edge with some other node, for example, right? And how do you choose it? You choose it randomly. Okay. So again, let me reiterate what we are doing. We choose a particular node. We reware. We keep on revarying edges based on the probability P. With probability P, you reware. You probability 1 minus P, you do not reware. Right? So when P tends to 1, it means that this is very highly likely that whatever edge you choose, it will be eligible for revarying. So when P equals to 1, P tends to 1, the regular lattice tends to become a random network. The lattice was formed in a very systematic way, but you keep removing, you keep randomly connecting, you keep removing the connection which is present in the random in the lattice, and you keep adding connections randomly, revarying connections randomly. Remember, we are not adding any edge, we are just revarying edges. So total number of edges which is there in the network will remain same. So what does it indicate? It indicates the average degree will always remain same, because the sum of degree, we all know that sum of degree is 2 into number of edges. So number of edges is fixed, therefore the sum of degree would always be fixed. Therefore the average degree would always be fixed. Clear? Clear? So if you do that, if you follow this formation, this kind of graph formation, what would happen is that you see you will see a structure like this. What is this? Let's look at it carefully. Okay. So if you keep on revarying this, and if you increase the probability of revarying, okay, so x-axis is the probability of revarying edges, and y-axis is some normalized value, right? So in this case, we consider two values, which is the clustering coefficient and other is the average path length, because clustering coefficient is associated with the is something that you wanted to adjust, right? Random network was not able to fit the regular clustering coefficient, therefore we shifted into lattice model. So lattice model was successful in capturing the real world clustering coefficient, whereas in case of average path length, random model was very successful, but lattice was not that successful, right? So the idea was that, can we have an intermediate stage between random network and a lattice model which satisfies both these properties, clustering coefficient and average path length? Okay, so if you plot, right, if you plot the value of clustering coefficient and average path length, you fix n, number of nodes is fixed, you keep on increasing this p, right? Now what would happen? Let's look at this particular curve here, plot here. Now this plot is basically related to clustering coefficient. Okay, now what is cp? Cp is the clustering coefficient at a particular p value. And what is cp0? Cp0 is the clustering coefficient at p equals to 0. That means in this point. So the denominator cp equals to 0 means you have the clustering coefficient when p equals to 0. Now remember, when p equals to 0, it is basically a regular lattice, because we started with p equals to 0, a regular lattice, and we keep increasing p, and p equals to 1 means basically a random network. So cp equals to 0 is what? This is 3/4. We have already seen. This is very high. This is very high. right? So this ratio in this particular curve corresponds to the ratio where the new denominator is fixed, which is 3/4, which tends to 1. Okay, and numerator will change as you increase p. So at p equals to 0.1, you have a network structure, right? And you measure clustering coefficient. At p equals to 0.2, you have a network structure, and you are moving from random from regular lattice towards random network, right? At p equals to 0.3, you have some network, and you measure Cp. Okay, so you see that this ratio is almost 1, right? Almost 1. Suddenly around 0.2 or so, p equals to 0.2 or so, it starts decreasing, right? That means that till p equals to 0.1 and 0.2, the clustering coefficient of the resultant graph is almost same as the regular lattice, which is quite high, right? Now let's look at this curve. Now this curve corresponds to again the ratio of LP by LP0. So LP0 is the average path length at p equals to 0, and what is LP? LP is the average path length at a certain p. So again, at p equals 0 means you have the regular lattice, right? So you see that immediately, once you start changing p value, immediately this ratio decreases. What does it mean? What does it mean? So immediately this ratio decreases. Now this is fixed. This is always fixed, right? That means that this value starts decreasing. Therefore, the ratio also starts decreasing. And this is an immediate effect, right? As compared to the clustering coefficient, where it starts decreasing, after p equals to 0.2 or 0.15, it starts decreasing immediately. Okay, so now you see that around this region, okay, this region, what are the properties? Right, in this region you have certain networks, right? What are the property of that? What are the properties of the network? The network has reasonably high clustering coefficient, right? And the average path length is again a kind of a it scales with it scales with n, not that high, not that low, right? So Watson and Strogat, so they said that this region, whatever network you generate, they kind of follow the real world property. That means kind of high clustering coefficient, and the power law would be around log of n, right? You can theoretically also prove that. I'm not going to the theory of this, but you can theoretically prove that with certain values of p, it starts looks like this, the average path length. Okay, so they said that if you really want to generate a real world type network using Watts-Strogat model, you start with a lattice network. You keep on increasing, and around the p value of 0.01 to 0.1 or 2 or 0.2, you whatever structure you get, that would be quite similar to a real world network. Yeah, question.
Sir, I had a doubt. Sir, what happens when we increase the rewiring probability? How does the graph then looks like?
So when you start increasing the rewiring probability, what does it mean? It means that whatever so what's the process? You choose an edge, right? And you decide whether you will rewire or not, right? If the probability is very less, you will not rewire. If the probability is high, you will rewire it, right? Now, if the probability value is very high, that means whatever edge you choose, you would always decide to rewire it. Right? The probability value is high. That means whatever edge you choose to decide whether you rewire or not, you will always rewire it. And rewiring process is random. Rewiring process is random. That means you start moving towards a random network. In a regular lattice network, the rewiring was very systematic. You only connect a particular node to k-1 nodes in the left side and k/2 nodes in the left side and k/2 nodes in the right side. But in case of random network, right, you just rewire it randomly. So when p goes to 1, the graph is completely a random graph. Okay. So Watch-Together model, the problem is that it doesn't have any guarantee in whether the particular network follows the the scale fee property, because it's ultimately, you know, from regular lattice you are moving to random networks. So in the interspectrum there is no concept of power law distribution, degree distribution, right? So now this is an example graph, right? So there was this archives co-authorship network where nodes are co-authors and nodes are authors, and two nodes are connected if they co-authored in some paper. And this data was collected from archive repository, right? And three things were ran. One is the random network model, right? The other is the Watch-Together network, and the third one is the real citation, real co-authorship network. Okay. Now let's look at the plots. So this red line corresponds to the real network. You see here in the log scale, it is almost power law, right? The blue line corresponds to the random network. As you see here, this is kind of a binomial types distribution. So Watch-Together model as well, it doesn't follow power law at all. Okay. So the degree distribution, we don't have control. We can't control power law. We can't make the degree distribution power law for Watch-Together case and for random network case. Okay. So the next model that we discuss is the very, very famous model, which takes into account the factor that the network would always be following the power law degree distribution. Okay. So I hope you are understanding the evolution of the network growth model. So we started with the random network. We saw that it is small world, but it does not follow power law. It does not follow the clustering coefficient property. Then we moved to lattice network model, and there we see that the clustering coefficient property is followed, but the power law is not there, right? Then and it was also not a small world network. Then we moved to Watch-Together model, and the Watch-Together model, we have seen that it tries to, you know, make a balance between the two extreme, random and lattice, and clustering coefficient is still preserved, right? Average path length is still preserved, because in that region average path length is order of log n, and clustering coefficient is also quite high. But the problem is it doesn't follow the power law degree distribution. Now we need a model which would take care of all sorts of properties, right? So now this is called Bharavasi-Albert model, right? The famous physicist Bharavasi and his student Albert. So they proposed this model in 2000-2002, around that time. This is also called a preferential attachment model, and it is also called Rich-Gates-Richer model. We will discuss why this is called Rich-Gates-Richer model. And the beauty of this model is that it is guaranteed to generate a scale-free network, right? Where the degree distribution is a power law degree distribution. Now let's look at the design principle of Bharavasi-Albert model. Okay. So what's the network formation property? So what's the network formation stage? Okay. So initially we assume that now remember, this is unlike other algorithms, other models like random graph model and other models, where we assume that the number of nodes is always fixed. Number of nodes is always fixed, and we basically think of how to rewire nodes, right? But in case of Bharavasi Albert, this is very similar to the way a real network grows. That means it's a temporal network. We consider that each node will come at every timestamp with some edges, and that's what a real network grows. The number of nodes is not fixed, not static. In case of real network, nodes will come, right, and the associated edges get connected to the existing nodes and so on and so forth, right? But I agree that in real world network, node can also be deleted, edges can also be deleted. Bharavasi Albert model doesn't consider this because this was an old model. There are a lot of follow-up works for Bharavasi Albert model. There they considered node deletion, edge deletion, and so on. So the Bharavasi Albert model, simple idea that you start with a small number of nodes and you keep adding nodes and associated edges into the system and see how the degree distribution varies. Okay. So we start with a limited. We start with the limited number of nodes, right? And let's assume that this is M0. So M0 is the number of nodes at time 0th time, initial. Okay. Now you can assume that there are some edges. There are some edges among these M0 nodes, right? And this number of edges is basically very small. So you can assume that there are some edges. You can take that factor into account for the rest of the calculations. But this number of edges is so less, right, that you can also ignore it when you increase the timestamp, right? When t tends to infinity, this number of edges, initial number of edges, doesn't matter, doesn't make much sense. So let's assume that there are some edges, but let's not consider those edges in the calculation. Okay. So we start with small number of nodes M0, right? At every time step, right? A new node joins with M degree. So initially you have M0 number of nodes here. A new node joins here with degree M, right? So at timestamp 1, a new node joins with degree M. At timestamp 2, another new node joins with degree M, right? And so on. Another drawback you can see here that the degree is same. A new node coming in and the degree is same, but that's again a kind of simplified version. You can try to generalize it, right? So now the question is, this M edges, how these M edges will be connected to the existing nodes? What's the attachment principle, right? Say for example this edge, whether this edge, because these nodes also have some they have some degree, right? So whether this edge will be connected to this node or this node, we don't know. So this is something that we will determine. What's the attachment principle, or what's the wearing principle? Okay. So the attachment principle says that a node is connected to a new node is attached to an existing node based on something called preferential attachment. Okay, preferential attachment, right? Now what does it mean? It means that that a particular node will prefer a new node will prefer an existing node whose degree is high. So preference based on the degree. In this Bharavasi Albert model, the preference was based on the degree. That means if the node has higher degree, if the node has high degree, it is highly likely that the new edge will be connected to the high degree node. Okay, so the probability that a new edge attached to an existing edge attached to an existing node with degree di is di by summation of di or dj, right? What is di? Di is the degree what should I say? Is just a degree, right? So what I'm saying is that right, that so assume that you have degree 1, degree 2, degree 3, right? And you have 5 nodes with degree 1, 6 nodes with degree 2, and again 5 nodes with degree 3, right? So P of di equals to 1 is 5 by 16. P of di equals to 2 is 6 by 16. P of di equals to 3 is 5 by 16. Okay. So as you see higher degree, it is highly likely that the new edge will be connected to the higher degree. But remember, this is probabilistic, so it is not deterministic. It in the sense like it would not happen that only a particular node with high degree will keep getting edges and edges. It's a probability, right? It may happen that in some cases other nodes with small degree will also get connected with the new edge, right? Is this clear? So this is called the reach gets richer principle, meaning that here the reach node is the node with high degree, right? And poor node with poor nodes are the nodes with smaller degree, right? So since this always prefers higher node, it is highly likely that reach will get richer and poor will get poorer. Okay, now let's look at different properties of this case. Okay, different properties of this particular model. So
Sir,
yes.
I had a doubt. Sir, only the nodes which are getting more nodes attached to them, only they will keep on increasing. How will it be uniformly distributed? I'm not able to understand.
This is not uniformly distributed. Who said?
No, sir, that means only the nodes which are getting, the new nodes which are getting added to the ones which are having higher degree, only they will keep on growing.
No, this is probability. That's what I mentioned. That with probability, say for example in this case, right? Let's assume that this is 1. Okay. So let's assume that okay. Okay, so a network looks like this. A new node comes in. Okay, there are 2 edges. So this node has highest degree, right? Followed by, say for example, this node, right? This node. So right. So this node, it is highly likely that this edge will be connected to this node with some probability, and the probability is proportional to the degree. Now, it is highly likely doesn't mean that every node every edge will always be connected to this node. It's a probability. So with probability P equals to, say, with probability 5 by 16, for example, this edge will be attached to this node. With probability 1 minus 5 by 16, this edge will be attached to other nodes. So it is not the case that a node with high degree will always attract edges. Of course, with higher probability that it will attract edges, but other nodes will also get chance, because ultimately the process is a probability. It's a coin toss, biased coin toss. Please understand, this is not a deterministic process. Okay, it's a probabilistic process. Okay. So P of di. Okay. How do you measure it? This is I mentioned this is di summation of dj, right? Where dj is where j ranges from all sorts of degree. For example, degree 1, degree 2, degree 3 in this case. Now, what's the value of this? Tell me, this is sum of degree. Now, sum of degree is what? 2 into number of edges, right? How many number of edges are there in the graph? Tell me. How many number of edges are there in the graph? So every node comes in with a degree m, right? At a particular time t, how many nodes have been added at a particular time t? M into how many nodes have been added at a particular time t?
M into T and total.
How many nodes have been added?
Nodes?
Yeah.
T nodes.
T nodes. No?
T nodes have been added, and there are already M0 number of nodes. So total number of nodes at time t is M0 plus T, because at every time stamp only one node is getting added. And how many number of edges are there? M into T, because T number of nodes and each node has M edges. So M into T number of edges. We are ignoring initial edges. I already mentioned, right? So 2 into number of edges means 2mt. Right? Right? I hope this is clear. Is this clear, guys? So this is di by 2mt. You can unmute and let me know, okay, if this is clear or not.
Yes.
Now let's look at how the degree evolves, okay, because we are interested in degree distribution, right? And we want to see whether the degree distribution follows the power law or not. Okay, so in order to do this, we will follow two ways. One is called continuum approach. The other is called master equation. Okay, so let's start with continuum approach. So both these approaches are used to analyze the degree distribution of a particular network. So we will look at the continuum approach first, and then we look at master's equation. Okay, so let's start with continuum approach. In the continuum approach, so let's start with this, right? So P of probability of of an edge of probability of a node with degree di, will be attached to an incoming edge is di by 2mt. Okay, so what's the rate of change of degree di? How do we measure the rate of change? How do we measure the rate of change of degree di? Any idea?
So we will find the derivative of it.
Very good. So we'll take the derivative, right? Del di by del t, right? How do we and what is this value? Tell me, what is this value? At every time when a new node comes in with m number of edges, how does it affect degree di? What's the rate of change? How do you measure this? this would be m times p of di, right? So m is the number of edges which are coming, right? Which are coming with the new node, and pdi is the probability of is basically the probability of nodes with degree di at that time. So this would be the rate of change of degree di. Okay. Now this is m times, we already know that pdi is this one. So di by 2mt, which is di by 2t, right? So we get del di by del t is di by 2t, right? Which is del di by di is del t by 2t, right? So what we do now, very obvious, we take the integral in both sides, right? And we take the integral where the limit is di ti, right? I'm telling you what's the meaning of this di t, right? Ti t. Okay, what is the meaning of ti? Ti is the time when node vi has joined the network, right? And what is di ti? Ti is the degree of node vi at ti. Okay, so this is the degree of node vi at ti, and this is the degree of node vi at t. So therefore we integral the time from ti to t, right? If you do this, you will have this is di, right? This is di. So you will have ln di t by di ti equals to half ln t by ti. Okay, so this would be di t di ti equals to square root of t by ti, because this would be like this. Okay, and log, both the sides will cancel out. So therefore you will have dit is di ti times t by ti to the power half. Okay, let's denote beta as half. So this would be d ti di t t by ti to the power beta, right? So this beta, which is generally half, is called the dynamical exponent. Dynamical exponent, right? So now think about it. So this indicates that the degree of vi at time t. Okay, so this is ti. Okay, this is ti. This is degree of vi at time t. It is determined by this factor. Okay, so now what is the value of this one? Tell me, what is the value of this one? This is di ti. What is DI/TI? Degree of node Vi at time t, right? And what is degree of node Vi at time Ti? Now, what is time Ti? Ti is the time when Vi has joined. So that means this is the degree of node Vi when it has joined. Now, when Vi has joined, what's the degree of Vi? Tell me. When Vi has joined, what's the degree of Vi?
It would
M?
be M, sir.
M, because a node joins with degree M always. So this would be M times theta. Right? Now let's look at this equation very carefully.
Sir, I have one doubt.
Yeah.
Sir, as you said that a degree always joins with the M, a node always joins with the M degree. Sir, ये assumption या फिर इसका means
This is the assumption. This is the assumption.
Okay.
This is the assumption of Bharavasi-Albert model, that a node always joins with degree M.
Okay.
So let's look at this equation very carefully. Right? It says that DIT is proportional to T power beta. What does it mean? What does it mean? So the growth model also, this is also a power law. Something changes with the power of something, right? So it is also a power law with respect to the time parameter. We are not done yet because we need to prove that the degree distribution follows a power law. This is not degree distribution. Okay, so it says that the growth of a degree also follows power law with respect to time t. This is the first conclusion that we can draw. The second conclusion is that DIT is inversely proportional to TI, right? From here, inversely proportional to TI. What does it mean? What is TI? TI is the time of joining of the node. TI is the time of joining of the node. It says that if TI is high, if this is high, this is low. That means what? TI is the time of joining. That means so the difference between T minus TI, right? That it means that someone, now tell me, what's the meaning of this? What's the meaning of this?
So the nodes which join late will have a lower degree.
The node which join late, tell me, if the node joins late, then what would happen?
They would have lower degrees.
They would have low degree. That means
yes,
the node
sir.
which joins early will have high degree. Right? Yes or no? If the node joins early, they have high degree. Okay? And this is called first mover advantage. Okay? This is called first mover advantage. All right. So now let's look at the other properties. Okay. So these two properties are very important, and we will look at it again later. So now, so note that at timestamp t, okay, again, what's our aim? Our aim is to derive the property pk, and we'll see whether pk is proportional to something to the power minus alpha or minus beta or not. Pk is the degree distribution. Okay. So when a particular at a particular time t, okay, at a particular time t, how many nodes are there? Again, m0 plus t number of nodes are there. M0 is the initial number of nodes, and t is the total number of nodes at time t. T is the number of nodes which have joined till time t, right? And so this is the total number of nodes. And how many number of edges are there? Number of edges. is empty, right? We have already seen. So let's assume, let's again look at some of the notations. P of di. What is P of di? P of di we have already seen. P of di is the degree of node vi at time t, for example, right? So what is this? What is right? Right. Sorry. This is di, right? Di is the degree of node. Di is the degree of node vi at time t. Okay. P is the probability. So let's look at the cumulative probability. Cumulative probability that a particular node I has a degree di at time t. Okay. What does it mean? It means that this is the probability that a random node vi has degree less than k, at time t. Okay, this is the probability. Okay, so right. So how do we measure this? We have already seen. Let's look at this calculation. Let's do the calculation separately. dit less than k, right? And we have already seen that dit is nothing but this one. Okay, right? So this is m into t by ti to the power half less than k, right? We can calculate some, we can do the calculation. We can see that ti is greater than m by k to the square into t. Okay, if we move ti to the top and k at the bottom, you see that this looks like this. Okay, so this is same as this one. Okay, so we can replace this probability by this one, ti greater than m by k square t. Okay, now this is same as 1 minus p of ti less than equals to, right, m square k square t, because greater than this is same as less than equals to this, right? Okay, so now let's look at it. Now this part is a little bit tricky. Now let's look at this is very carefully. Okay, what is p of ti? What is ti? This is a density function. Okay, this is a density function. What is p of ti? Probability that a particular probability. So what does it mean? What is p of ti? Tell me. Any idea what is p of ti? Probability of a particular timestamp ti. Is this uniform or what? Is this a uniform probability or what? Is this a uniform? This is a uniform probability, because at every time we assume that only one node comes in. And a system with n nodes, this probability is 1 by n. Right? Which is nothing but 1 by m0 plus t, total number of nodes. Okay, so now again, go back to this part. Okay, we are interested in calculating this one. We are interested in calculating this one. Now tell me, if this is an if P of t, if the density function is uniform, then what is the value of this cumulative part? Is it essentially cumulative? If P of ti is uniform, then what is the value of this one? Any idea? It's a uniform, and we are interested in this range. Okay, this would be what? This would be this particular element times this, because at every right, because at every time step, you have 1 by n here, 1 by n, 1 by n, 1 by n, 1 by n, and how many times we are calculating? We are calculating is till m square k square by t. So this would be 1 by 1 minus, okay, 1 by m0 plus t into m square t by k square. Okay, these two things are same. These two entries, these two things are same. So this implies that again, if I write it down clearly, this would be, so I am writing this part again. So P of dit less than k equals to 1 minus m square t by k square m0 plus t. Okay. So this is cumulative. Okay. From this part, how do we get the density function? We need to take the derivative, right? So d dk of P dit less than k is d dk of this part, right? If you do the math, you will see that this would be 2 m square t by k cube m0 plus t with respect to k. Okay, so this is pk, because from here we basically take the from distribution function we get the density function, right? We take the derivative, and this is pk. This is non-cumulative. Okay, so with as t tends to infinity, as t tends to infinity, what would happen? This would be pk would be same as 2m square by, because in that case this and this part would be same, because in that case t would be very less than equals very greater than equals to m0, right? So the m0 plus t would be t, right? So we get this one. So you see that pk is proportional to k to the power minus 3. Therefore, the degree distribution follows the power law property. Okay, and therefore it is scale free. So from the continuum theorem, we have shown that the degree distribution follows power law, and the coefficient is alpha is minus 3. Okay, you can use the same trick with master equation. We'll discuss later that with master equation you can also show that this follows a power law. The degree distribution follows power law. Okay, so now we will discuss the second approach, which is called the master equation, to derive the same phenomena that the Bharavasi-Albert model follows power law degree distribution. Okay, So we have seen how continuum approach can be used for deriving this one. So we'll discuss how master equation can be used for the same purpose. Remember, these two approaches are used in general, for proving the degree distribution, the type of degree distribution across different models. This is not specific to any particular model. Okay, this is a generic approach. So master equation. Right. So this is an alternative approach, as I mentioned, alternative way of computing the degree distribution. So again, here, let us define some important notations. So n of d comma t is the number of nodes of degree d at time t. Okay. Therefore, and nt is the number of nodes at time t, at t. So therefore, the probability distribution, right, degree, the number of nodes with degree d, probability of nodes with degree d at time t is n of, right, this one. Okay, this is simple, right? So now in the continuum approach, we have seen that right, that P of di is di by 2mt. Okay, so in the continuum approach, we have seen that we represent P of d as d by 2mt, right? But here we will express PD in a different way. Okay, let's see. So an alternative expression of P of d equals to, now let's look at it, whether you agree with this or not, tell me. So P of t, I am writing in this way, is the sum of degree contributions, right? Is the sum of degree contributions, P of td, okay, for all d, right? And the contribution of that particular degree. Let's call it d dash. Okay. Okay. So what is it saying? It is saying that, you take the sum of all, what is d dash? D dash is a particular degree, right? And pt d dash is a probability of that degree. Okay. So what is this? What is this? This is the average degree, right? The denominator is the average degree, right? And the contribution of this particular degree in that sum is the numerator, right? Can we write in this way? Think about it. We can write same expression in this way. Okay. So now this equation is very important. This equation is very important. Now let's define two other measures. One is called outflux. Another is called influx. What is this? What is these quantities? Now, when a particular node with m number of edges, right? Remember, a node is getting added with m number of edges, okay, at every timestamp. So when a particular node enters the system with m number of edges, right, we would like to see the change of this quantity PD. We would like to see the change of this quantity after the appearance of this particular node. So what are the possibilities? There might be some nodes. So now think about it. Which nodes would affect PD after this addition? there are two types of nodes which would affect PD. One type of nodes whose degree is d minus 1, right? So say degree d minus 1, and if these nodes receive one edge, right, from this m edges, they would become degree d. Now, if they would become degree d, they would contribute to this PD, right? Similarly, if there are other types of nodes whose degree is d, if these nodes will receive one edge from the upcoming node, this degree, their degree will be d plus 1. So they would also affect this number because they are now not a part of the computation of PD, because now they become d plus 1, right? So these two types of nodes would affect the value of PD once when a particular node enters. Okay, so what is outflux? Outflux is a number of nodes, please listen to it carefully, number of nodes whose previous degree was d, right? Outflux means nodes which are moving out of a particular bucket. Okay, so number of nodes whose previous degree was d, and now it increases, degree increases to d plus 1. So they would, so when you compute PD, we should not consider these nodes. Okay, so now these are outflux. Remember, these are number of nodes. Okay, now what is influx? Influx is the opposite one, number of nodes that had earlier degree d minus 1, and now because of the addition of this new node, right, degree becomes d. Now these would be considered to calculate PD. Okay, so when we look at the change, okay, change in the number of nodes of degree d, right? So we basically need to understand the change. The change is outflux minus influx, right? Or the other way around, it doesn't matter. So or the other way around, you can write it as influx minus outflux, because these nodes will be added, and these nodes will be added to n d comma t. Okay, and these nodes will be deleted from n d comma t, right? Okay, we are interested in the change in this number, right? So now let's look at this quantity again. Okay, this quantity again. So we have seen PD is d PTD by, now tell me what would be the value of the denominator. So denominator is the average degree, right? Average degree is nothing but sum of degree is 2 into number of edges. So 2m t. Now, since this is average, so this would be divided by the number of nodes. How many nodes are there? There are t number of nodes, because at every timestamp only one node is added. Right? So this is 2m. Okay. Now PD, this is a very important equation. Okay. So now think about it. So Now remember, there is no parallel edge, right, in this graph. So two nodes are connected by only one edge. Okay. So the number of nodes, now tell me, when this m number of edges are coming in, the number of nodes with degree d, right, gaining at least one edge, because more than one edge is not possible. So gaining one edge, right, due to the addition of new node. What would be the number? M number of nodes, m number of edges are coming. How many number of nodes with degree d will be affected by this? Because m number of nodes are m number of edges are coming. Remember, since there is no parallel edge, right? So if each of these edges will be connected to only one node, so this m number of edges will affect m number of nodes, right? So this m number of edges will be connected to m number of nodes. Now some of these nodes would be degree d, right? So how many nodes will be affected? So m into PD, right? Because PD number of nodes are there with degree d. So if total is m and this fraction is the nodes with degree d, therefore this would be the number of nodes with degree d which will be affected. Now this is m, so I'm replacing PD by this. To m to mm cancel out, so we have d 2, right? So what is this quantity again? This quantity is when a particular node is joining, how many existing nodes with degree d will get one edge from the new node, from the upcoming edges, right? So this is the number. Okay. So now again, let's look at influx minus outflux, because this is the number which we are interested in. Okay. So now tell me, so we have defined something called PTD, right? What is PTD? PTD is the fraction of nodes with degree d at time t. Okay, so we define something called PTD, n. What is this? Fraction among n number of nodes, right? What's the fraction of nodes at time t with degree d, right? So we define this. We just kind of simplify this notation by P of d comma n. I'm not using the time concept t at this moment, because let's assume that we are computing this influx minus outflux at a particular time t. So therefore t is fixed, right? So we are interested in this quantity, P of d comma n. What is P of d comma n? Again, probability of nodes with degree d when the total number of nodes is n. Okay, so influx, again, what is influx? Influx is number of nodes with degree d minus 1 which has got affected, right, and became degree and became nodes with degree d, right, at this time, and outflux is the other way around, right? So in general, influx is the number of nodes at that particular point whose degree is d. Okay, so remember we had n number of nodes at time t. Okay, and a particular node has arrived, right? Therefore, now the total number of nodes is n minus 1, right? Now, among this n minus 1, how many nodes have degree d? That is influx. That's the quantity that we are interested in. So, can I write in this way? N plus 1 times P d n plus 1. Now, this is influx. What is the meaning of this? This is the number of nodes with degree d when the total number of nodes is n plus 1. A new node has arrived. Therefore, the number of nodes has increased to n plus 1. Now, within this set, how many nodes have degree d? Right? And what is the outflux? The outflux is n p d comma n. What does it mean? It means number of nodes when the node has not joined, the new node has not joined. At that time, the number of nodes was n. At that time, what's the number of nodes with degree d? Because this number of nodes will now become d plus 1. Okay, so they would be deducted from the system while calculating influx minus outflux. Right? So this is one way of writing influx minus outflux. Now let's look at another way of writing influx minus outflux. Right? So let's look at this equation again. Okay, this is a little tricky. Okay, so it would be great if you carefully understand what I'm saying. So let's go back to this equation again. What does it say? So it says that when a particular node has arrived with degree m, right, with m edges, right, what is the number of nodes with degree d that would gain one edge? So this is the number of nodes that would gain one edge. Okay, so now influx. So influx means we need to look at those nodes, right, which was earlier of degree d minus 1. Those nodes will become d. Those nodes will become d. The degree of those nodes will be d now, right? So here where I replace d by d minus 1. So d minus 1, right? P d minus 1, right? Comma n, you can write comma n, right? By 2. I'm writing this PTD in a different way. Okay. So this many number of nodes now would get an edge and become a part of D family, degree D family. Okay. And similarly, outflux we can write this way: D PD by 2. Because this many number of nodes at that time had degree D. Now those nodes will have degree D plus 1, so they would be deducted. Okay. Now this is the equation. So the equation is n plus 1 P D comma n plus 1 minus n P D comma n equals to D minus 1 P D minus 1 M by 2 minus D P D. Okay, you can write it as n plus 1 by 2. Okay, now when n tends to infinity, right, when n tends to infinity, all these quantities P of D minus 1, right, M, this is n, right, D of M minus 1 n, right, P of D n plus 1, right, P of, right, D n, right? All those notations, from all those notations, you can ignore this n part, because n plus 1, n minus 1, when tends to infinity, all are same, right? So again, I am simplifying the notation. I will ignore the term n plus 1, n, right? N from this equation, and therefore I can simplify this by writing n plus 1 times PD minus n PD equals to d minus 1 p d minus 1 by 2 by d PD by 2. Okay, so if we do the simplification, you will see that PD would be d minus 1 by d plus 2 p of d minus 1. If you just simplify the equation, you will see this. Okay, so this is the equation. Now, so again, what is PD? PD is something that we are interested to determine. PD is the probability of nodes with degree d. Okay, so you see there is a recursive formulation. So PD is dependent on PD minus 1. Okay, so if we expand it, we basically need to unfold it. Okay, so now let's look at the corner case. So PD is d minus 1 by d plus 2 into PD minus 1 when d greater than m. What is m? M is the number of edges which are coming into the system, right? Now think about it when d equals to m. When d equals to m, what would happen? When d equals to m, what does it mean? What does it mean? It means that when a particular node is coming in, what would be the fate of nodes with degree m, right? If we want to calculate P of m, P of d equals to m, right? When you want to calculate P of m, okay, how do you calculate it? So again, this is influx minus outflux, right? Influx minus outflux. So influx would be what? Tell me, what would be the value of influx? What would be the value of influx when d equals to m, right? So d equals to m means I can rewrite this equation as n plus 1 p of m, right, minus n p of m equals to influx minus outflux. So what would happen? How many number of, tell me, this is very important. When a particular node with m number of edges are arriving, right? There are some already existing nodes, right? N number of nodes, right? And remember, we assume that every time a node enters, it will have a degree m, right? So how many number of nodes will have degree m? Because we are interested in PM, right? We are interested in number of nodes with degree m at this time. How many number of nodes will have degree m when a particular node enters?
Just a node that enters.
Exactly, very good. So just the node which has entered, because for the other nodes, the degree is always at least m. Those nodes have already entered, their degree is at least m. This is undirected degree, right? So degree is at least m. So just the node which has entered, that node has degree 1, degree m. So influx would be 1. And outflux is something we need to calculate, right? To calculate outflux, what we do? We Again go back to this equation, right? This equation. So this would be m times pm by 2, right? So m times pm by 2. Okay, so if we simplify this, you will see that this m pm here m pm will cancel out, so we have pm equals to 1 minus m pm by 2, which is pm equals to 2 by 2 plus m. So when d equals to m, you have 2 by 2 plus m, right? And when d less than m, is not possible, because there is no node with degree less than m. So this is 0. Okay. So these corner cases will be used to unfold this equation, recursive formula. Okay. So let's unfold it now. So PD equals to d minus 1 by d plus 2 PD minus 1. Okay. So I'm replacing now. So PD minus 1 would be what? Bolo? D minus 2 by d plus 1 p d minus 2. I'm replacing d by d minus 1, right? So this would be d minus 1 times d minus 2 by d plus 2 d plus 1 p d minus 2, right? So you keep on unfolding and you stop when when you have p equals to m, because p equals to, d equals to m, because d equals to m is a corner case, right? So so if we do that, this would be d minus 1 d minus 2 dot dot dot. What's the last term? What would be the last term? So d minus 1, you see d minus 1 here, d minus 2, you see d minus 2 here. If it is m, then the last term would be m in the numerator. Look at the denominator. So d plus 2 d plus 1 dot dot dot. When this is d minus 1, this is d plus 2, that means d minus 1 plus 3, right? So this plus 3, again d minus 2 and then d plus 1, so d minus 2 plus 3, right? So if it is m, this term would be m plus 3. Okay, so d minus 1 d minus 2 dot 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 m d plus 2 d plus 1 dot 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 m plus 3. Now pm equals to 2 by 2 plus m, so 2 by m plus 2, right? So this is the equation now. So now what would happen? Right? Now tell me what would happen. Can you see some common elements in the denominator and numerator which you can cancel out? You can see here, right? So d plus 2 you can do this one. So this is what? This is d plus 2 d plus 1 d minus 1 d minus 2 dot 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 m plus 3, right? and you have d minus 1, d minus 2, dot 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 m. Okay, so right, m plus 3, and you also have m plus 2 because m plus 2 is here. It's m plus 2, right? 2. So m, so from d to m, you can cancel out, right? You can cancel out. So if we do that, you will have m.
So we can cancel out
into
from d minus
m
1 to
yeah, d
m
minus
plus 2.
d minus 1 to m plus 2. Yeah. So if we cancel out d minus 1 to m plus 2, so in the numerator part we will have m and m plus 1, right? And the denominator part we have d into d plus 2 and d plus 1, right? Times 2. Agreed, Shashank?
Yes, sir. Yes, sir.
So you see here that PD is proportional to d cube. You see here d power minus 3, right? Inversely proportional. So
Yes, sir.
right. So it means that it follows power law, where the coefficient is minus 3. Right. So this is not that tough, but the proof is a little bit tricky, particularly this influx. So this equation is the main equation. This equation is the main equation. If you understand this one and this one. Okay, you go back, read the book, you will understand even more details, the derivation. So this is about Bharavasi Albert, and you see that in both the approaches, we have derived that PD is proportional to d to the power minus 3. Here also we showed that PK is proportional to k to the power minus 3. Okay, so now let's look at the problems, the limitations of Bharavasi Albert model. Okay, so the first limitation is that at every time step, there is only one node coming in. Okay, and if multiple nodes join at a particular time, then what would happen? We do not know. I mean, how do we process those nodes? Because at t, assume that 5 nodes are joining. So how do we sequence it? Because it needs some sort of sequence, right? That this node will be processed first, then this node will be processed, then this node will be processed. How do we sequence it? How do we sequence them? So that is not clear. The second problem is that it's a linear model in the sense that the number of nodes attached to a particular network is constant over time. Right? At every time there is only one node coming in. Right? Which therefore it's a linear model, but real world networks may not be linear. In both the third problem is that in both the derivations we have seen that the degree coefficient is always minus 3, right? But I have already mentioned that in real world cases it varies from minus 2 to minus 4, in fact minus 1 to minus 4 sometimes. So Bharavasi Albert model is not generic in the sense like it is not able to explain varieties of networks. Okay. So the fourth and fifth problems a little bit interesting. So the fourth problem is that it always prefers older nodes. It always prefers those nodes which have high degree, right? But think of real world situation, right? Let's say think of a actor network. So in film network, actor network, movie network, where two actor or one actor or one actress, right? They work together, right? In a particular film, a particular movie, you can create an edge, right? So the degree of a node in that actor network indicates that how many movies this particular actor has participated. has acted, right? So we all know that as the time goes, right? I mean, there are exceptions, but as the time goes, actor, actress, they, you know, they became, you know, they start becoming less popular. Okay, young ages, right? When they are young, they get they tend to get more movies, tend to act in multiple movies. But as the time goes, you know, their popularity also decreases, right? So there is not only actor actress network, but also, you know, for scientific papers as well. So papers which are old, most of the old papers, they do not, you know, get citations over time, right? But Bharavasi Albert model says the opposite. So this kind of phenomenon cannot be explained using Bharavasi Albert model, right? Instead, what I'm saying is that there should be a decay factor associated with the age, right? The real age of a particular node. That as time goes by, it should the decay factor, you know, reinforces the, you know, the model not to attach any upcoming age to an old node, right? But that factor is not there. The fifth problem is that in real world network, right, there is also something called competition to achieve high degree, a competition to acquire a new edge which has just joined. Okay, so what do I mean by competition? So think about you know, again, scientific papers, right? Citation network. There are many papers these days which you see that within very short period of time, right, they gain a lot of citations, right? Because they have won the competition. They stand out the time constant, right? So and let's assume that, you know, there are politicians, for example, right? The young politicians who doesn't have much political background, but they join and they started ruling, right? So this competition factor, that a node will compete with others to acquire a particular age, to increase the degree, that competition factor is not there in the Bharavasi Albert model, right? So we will see there are, you know, a lot of models proposed later on, which are kind of advanced version of Bharavasi Albert model, where they considered the competition factor, the decay factor, and so on. But we, in our lab, we also did a couple of studies where we proposed models where we incorporated the notion of, you know, recency, right? Recency of a node. Now, recency is basically, you know, the time elapsed for a particular node since it joined the network and till the current time. Okay, the age basically. Now, you know, recency factor, competition factor, there are many other factors that are useful to capture different properties. Now, the problems in most of the models that we discussed so far, that they are evaluated based on 2-3 factors. So one factor is the degree distribution. They always, you know, look at you know, how to make the network small world, or, you know, power law degree distribution, or high clustering coefficient, or you know, outliers. And so there are 4 or 5 properties that they try to satisfy. Okay, but there are many such properties which they tend to ignore. And in the later papers, you know, papers published around 2005 to 2010, they showed that, you know, these 4 or 5 factors are good, but you also need to consider other factors, right? So if you're interested, you can look at some of these papers, but in the book also there are 3 or 4 additional models, like local growth model, right? That you can look into. Okay, so the last model that we discussed today is called price model. Okay, price model. What happened? price model. Okay, so now it is not that the Bharavasi Albert, were the first. Bharavasi and Albert were the first to explain the long tail, the heavy tail, or the power law distribution, right? So the search for such a long tail distribution network, power law distribution network, to explain the power law behavior started way back 1965. Okay, so D.J. Sola Prize. So right, so he was a physicist, come information scientist, and he was the father of the field called scientometrics. Scientometrics is a field which basically deal with scientific papers, scientific publications, right? Say H index calculation, I10 index calculation, impact factor. So whatever you do with the scientific publications, right? Patents, papers, though all those research come under scientometrics, and he is the father of scientometrics. So he started looking at this power law kind of degree distribution way back 1954, 1955. Okay, but at that time he was only restricted himself to citation network. At that time there was no social network or whatever, right? So so he restricted himself to citation network, where nodes are papers and citations are ages. Okay, and the reach gets richer phenomena, right? This phenomena was explained by him at that time, and he called this phenomenon as cumulative advantage, right? So cumulative advantage is basically the advantage that you acquire over time cumulatively by receiving citations. Okay, so cumulative advantage indicates the likelihood of a paper being encountered and cited by other papers. Okay, so he also proposed a model which is called as price model. Okay, now let's look at this price model, particularly in the context of citation network. Okay, so again, let's assume that you have nodes, scientific papers, and a particular paper is coming in, right, into this world, right, with out degree, because this is remember, this is a directed network, citation network, right? So out degree M. Now you may say that this assumption is false because nodes can have different out degrees. Now what is out degree of a node? Remember, out degree of a paper is the number of references, right, which are there at the end of this paper. That means number of papers which this current paper has cited. This is out degree, and in degree is the number of citations, incoming citations, right, that a particular node has received. Now when I say that citation, I basically mean to say the in degree. When I say reference, I mean to say the out degree, but these terminologies are used interchangeably. Okay, so you may say that okay, out degree can vary because one paper can cite 10 other papers, another paper can cite 20 other papers, so the out degree can vary, right? So he argued that yes, out degree can vary, but the average out degree, since the number of ages is same, right? So he argued that so let's say pk dash is the probability of a particular node with in degree k dash, and pk double dash is the probability of a node with out degree k double dash, right? So sum of in degree and sum of out degree would always be same, because this is just the 2 into number of edges or number of pages, because this is a directed graph, right? So he argued that out degree may vary, in degree may vary, but the average in degree or the average out degree of a system, average out degree of a node or average in degree of a node in a system, in a particular network is always fixed. Why? Because the total degree is fixed. So let's assume that M is the average number of edges that a particular node, are connected with when it joins. Okay, so he argued in this way that the number may vary, but the mean would always be constant because number of edges is constant. Therefore, let's assume that a particular, so therefore the argument that a particular node enters with an out degree M, right, and this M is fixed for all the other nodes, incoming nodes, is not an invalid argument as such. Okay, because in the mean sense, in the average sense, right, this is okay, right? So, and he also now the question is, when a particular node arrives, when a particular paper arrives with m number of citations, m number of references, how the existing nodes will acquire this edge? So existing nodes will acquire edges again based on the preferential attachment. Okay, but at this system, when the system starts, nodes do not have any in degree, right? So I said that each node, so the decision whether a particular edge will be associated with a particular node is dependent on that node's in degree, is proportional to node's in degree. That's why it is called rich gets richer. So a paper which has high in degree tends to receive more citations when new papers are coming in, right? But when the system starts, nodes do not have any degree, nodes do not have any in degree, right? So in degree is 0. So how do we resolve it? So he suggested that let's assume that in degree of every node at timestamp 0 is 1. Let's assume that all these nodes have in degree 1. Now, how do we interpret it? How do we justify this assumption? So justification is very simple. So he said that when a paper gets published, so the published paper itself is an indication of its citation. When a paper gets published, it means that assume that the paper cites itself because it has got published, so it has got some merit. So somebody cited this paper, somebody acknowledged this paper. So whenever a paper is published, it basically comes with a degree 1, in degree 1. So in degree at 0 for all the nodes is 1. Okay. So, right. So now how do we define P of K? Okay. P of K is, again, I am using the Master's theorem, right? The Master's equation that I mentioned here. Right. Okay. So PK is, so it should be PKT whatever, right? Summation of, right? But remember, for each node you have an extra degree 1, which is K0, right? So instead of K we write K plus 1. Right? This 1 is the additional degree that we always consider. Okay, so this is K plus 1 PK by, now what is this number? This is the average degree plus 1, right? Because this is KPK plus summation of PK, right? So this is K plus 1 PK by, now this is what? This is the sum of degree is number of edges. This is a directed graph, so the number of edges would be M, right? Plus this is 1, this is 1, this is sum of degree distribution. Okay, so this is the preferential attachment formula. So K plus 1 PK by M plus 1. Okay. So now think again, let's revisit. So once a particular node without degree M has arrived, right? So the mean number of new edges connected to degree k nodes will be what? P into M into pk, because M number of nodes will be affected and there are pk fraction of nodes with degree k, right? So this would be k plus 1. I'm replacing pk by this. This would be k plus 1 pk by m plus 1 times m. So this is same as the number of degree k nodes which will be affected as a new node enters. Okay. Right. Now, again, let's look at the influx minus outflux. Okay. We have already seen n plus 1 p of, look at here, right? I'm just copying this equation. So I'm just copying and replacing d by k, right? The same, other things remain same. So n plus 1 p k n plus 1 minus n p k n. This is influx minus outflux, right? So let's look at influx. Influx in terms of this one. Okay. So influx means degree k minus 1 nodes becoming degree k, right? So if you use this formula, this would be k into p k minus 1. I'm replacing k by k minus 1 because those number of nodes will be moved, right? N, right? Times m by m plus 1. This is influx. And outflux would be degree k becoming degree k plus 1. So this would be same as this one. Okay. So this is m by m plus 1 is common. So k p k minus 1 comma n by m plus 1 minus k plus 1 p k comma n by m plus 1. Right? Now this is true when k greater than 0. Right? What happens if k equals to 0? What does it mean? K equals to 0 means what? What is k? K is the in degree. Please remember, here k is not the degree. As like Bharavasi model, this is a citation network, directed graph. K is the in degree, right? We are interested in degree distribution, right? K is the in degree. So when a particular node comes in, right, what's the change of influx or what's the value of influx when k equals to 0? How many number of nodes are there with k equals to 0? How many number of nodes are there with in degree equals to 0 when a particular node comes in? Only one, because the node which is entering that nodes in degree is 0. Out degree is m, but in degree is 0. So this would be 1. And out degree we do not know. Out degree we need to calculate, right? So to calculate out degree, we use this formula again, right? We replace k by 0, so we have pk, right? So pk means p0 n, right, times m by m plus 1. So this is the value when k greater than 0, and this is the value when k equals to 0. Okay, so again we will let's assume that when n tends to infinity, right, n plus 1, n minus 1, they are all same, so we can ignore this. So therefore we rewrite this equation again. So n plus 1 pk minus n pk equals to two cases, m by m plus 1, right, k pk. I'm rewriting this equation, k pk by n plus 1 minus k plus 1 pk by n plus 1, right, when k greater than 0. When k equals to 0, this would be, right, this would be 1 minus p, p0 m by m plus 1, right? So let's consider this separately and this separately. So let's consider the second equation separately first. So this would be n plus 1. So pk, k equals to 0 means p0 minus n p0 equals to 1 minus p0 n by n plus 1. Okay, if you, so this will cancel out, this part will cancel out. So if you derive, you get p0 equals to m plus 1 by 2m plus 1. Okay, and similarly, if you adjust this equation, right, you will get pk equals to pk minus 1 k by 2 plus k by 1 plus 1 by m, right? If you know, adjust this equation. So we have two corner cases. This is one corner case when k equals to 0, when k greater than 0, you have this one, right? You see, this is again a recurrence formulation. So right. So let us unfold this equation again. Okay, so we have, now this unfolding is a little bit tricky, so look at it here carefully. So pk, so pk equals to pk minus 1 k by 2 plus k by 1 by m. Okay, I'm replacing pk minus 1 by corresponding value. So we have k into k minus 1 by 2 plus k by 1 by m times 1 plus k plus 1 by m, right, p k minus 2, right? If you go on and on till p0, you have numerator, you will have k into k minus 1. So this is k minus 1, we have k, right? So 0 means you will have 1 here, Okay, now let's look at the denominator, right? How would this look like? Denominator would be, what is the last term of the denominator? K plus 1 by m dot dot dot. Now look at here. When you have k minus 1, in the denominator you have k plus 2 plus 1, right? That means you are adding 3 plus you are adding 3 plus 1 by m with this term, right? So you have 0, so we have 3 plus 1 by m here. Okay, now I'm replacing p0 by m plus 1 to m plus 1. Okay, so now let's look at this derivation. So can we write this part? Okay, m plus 1 by 2m plus 1, can we write as 1 by 1 by m by 2 by 1 by m? What I've done, I have divided denominator by m, numerator by m, right? So I'm replacing this by 1 by 1 plus 1 by m by 2 plus 1 by m. Okay, so let us keep this part separate. Okay, so 1 by 1 by m. Okay, k into k minus 1 dot 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 1 by 2 plus k plus 1 by m dot 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 3 plus 1 by m 2 plus 1 by m, right? So what is this? This is factorial of k. Right? And let's look at the new denominator. Let's look at the denominator. So the denominator is what is the denominator? If we, just a minute, if we multiply 1 plus 1 by m in the numerator as well as in the denominator, okay, then how many terms are there? If you want to make it in terms of factorial, how many terms are there?
Sir, if we make it 1 plus 1 by m factorial in both numerator and denominator.
So just a minute. If I write it as k plus 1 plus 1 by m factorial. Sorry, k plus 2. Sorry. 2 plus k. 2 plus k plus 1 by m factorial, right? This is the last term. So if I want to write it in 2 plus a plus 1 by m factorial, I need to add some more term here till 1, right? Yes. So how many terms we need to add here? We have till 1 plus 1 by m. So we need to have 1 by m, then 1 by m minus 1, and so on. Right? Yes or no? So this part is what? This part is 1 by m factorial. So we need to multiply 1 by m factorial in both numerator and denominator. Then only we get this one in the denominator. In the numerator, we already have factorial k times, this one is what? This one is 1 plus 1 by m factorial. Right? Sasank?
Yes, sir.
So if we are done. So if we calculate it, so we know that this gamma function. I'm not sure whether you know this, but gamma function is a function which is related to factorial. So gamma of k is factorial k minus 1. Okay, right? Which is basically gamma of k is gamma of k plus 1 is k into gamma k, which you can easily derive. So gamma k is factorial k minus 1. So this factorial k is essentially gamma k plus 1, right? Or factorial 1 plus 1 by m is gamma 2 by 1 plus m. Okay, and this one is gamma what? K plus 1 plus 2 plus 1 by m. Just adding, so just 1 plus the factorial term, right? So I wrote entire thing in terms of gamma. Now there is another interesting property, is that there is another function called beta function. Beta a comma b is gamma a times gamma b by gamma a plus b. Okay. Okay, now look at this. This is so interesting, right? This is 1 plus 1 by m. You see here gamma a plus gamma b plus gamma a by gamma a plus b. So this is essentially beta, right? K plus 1, 2 plus 1 by m, right? So there is another property in the asymptotic limit, right? Asymptotic limit is beta function right? This is e to the power, can be written as is e to the power minus b. Okay, therefore here also in the asymptotic limit we have 1 plus 1 by m k plus 1 to the power minus 2 plus 1 by m. Okay, so we have derived that pk is proportional to k to the power minus 2 plus 1 by m. Okay, which is a power law, right? So it looks little tricky, but you should appreciate the way it was derived. Okay, so you see here that price model also follows the power law property, and with the exponent, and here the exponent is flexible because it is also dependent on m, right? If you vary m, the exponent will also vary. Okay, unlike Bharavasi Albert, where the exponent is always -3. So this is price model. So you know, Bharavasi Albert price models, these models are kind of similar because both types of models kind of endorse the phenomenon of preferential attachment. But now let's think of, you know, network like protein-protein interaction network. So in protein-protein interaction network, there is no reason that a protein will interact with another protein having higher degree, right? This is meaningless, right? So, most of the biological networks, although they follow power law, but they are not explained by preferential attachment. Okay. So for those models, what are the other explanation model for those network, right? So the Price model was the base of models like Bharavasi Albert, models like other preferential attachment model. So John Kleinberg, from Cornell, so he proposed a model called vertex copying model. Okay. The vertex copying model, I'm not going into the details of vertex copying model. I'll just give you a glimpse of what is copying model. So vertex copying model is an interesting model which you can use to explain the biological network, power law behavior in biological network. So vertex copying model says that you can also explain power law behavior of citation network as well using vertex copying model. It is generic. So vertex copying model says that, let's assume you have a network like this, you have an initial network like this, okay? Okay. And let's assume that a new node is coming in with degree 3, out degree 3. So it is called vertex copying because what it does is that when the new node comes in, it chooses an existing node uniformly at random and copies its edge edge distribution, whatever it means. That let's assume that this is A, B, C, D, E, and this new node V is coming in, okay? And let's assume that the node V copies the edge distribution of node E. The node E has been chosen uniformly at random, so its edges will be copied. It means that since E is connected to B, D, and C, V will also be connected to B, D, and C. Okay. Now, what happens if E has degree 2, for example, and V has degree 3, right? So 2 of V's edges will be copied based on E's degree, right? And the remaining edge will be copied. The remaining edge will be copied again based on another randomly chosen node. So you have just copied E's edge distribution, right? You are exhausted. Now you choose another node, for example, like C. Now let's assume that C is connected to B and A. So this remaining edge will be connected to either B and A, again uniformly and random. Okay, so this is vertex copying model, and this can also be used to explain citation network. For example, let's assume that you are writing a paper, and when you write papers, write a paper, you look at other papers, right? And you look at where those other papers, to which papers the other papers have cited, right? Say for example, I am doing literature survey, and I have seen that paper X is relevant to me, right? I will definitely cite paper X, right? And what I will do, I will cite those papers which paper X has also cited. Some of those papers, not all. So we kind of copy vertex. We kind of copy the associated edges of the vertex. Okay. This is called vertex copying model. You can derive its degree distribution. You will see it again follows power law, right, and so on and so forth, right. There are many other recent models like local world model, right, network growth model with some accelerating growth and so on, which I'm not covering in this lecture. You can look at the book and you get ideas about the recent models. Okay, so this brings us to the end of this chapter. Thanks.